Yes, good morning. We shall begin with today's aspect. That is, we are going to study today the magnetic properties of lanthanides, then the colored ions, then lanthanide contraction, and if possible, the separation of lanthanides. I would like to give you certain brief ideas regarding the yesterday's electronic configuration and oxidation states. While studying electronic configuration, we have arrived at that after lanthanum, the 4f orbital becomes decisively more stable, and hence from cerium onwards, the incoming electron occupies the 4f orbital. And at lutetium, atom number 71, where 4f orbital has been completely filled. So next choice for incoming electron will be 5d1. 6s orbital is filled at barium, that is atom number 56, and we have started filling all the electrons in 4f electronic subshell. So the characteristic electronic subshell for lanthanides is 4f. A question of the type sometimes may be asked that all lanthanides having dash number of incomplete shells. Your answer should be 3 incomplete shells. Which are those? 4f, 5d, and 6s. So we should remember that all lanthanides are having 3 electronic subshells which are incompletely filled. So this is the correct answer. Now, after the completion of electronic configuration, we have moved to the oxidation states. While assigning oxidation states, we have given much more emphasis on the common principal or major oxidation states, that is a +3. All lanthanides, they do display +3 oxidation state on account of the group valency, that is a 3, because all lanthanides, they belong to group 3rd B of the periodic table, and hence group valency is always attributed. Some elements, they do display +2 as a minimum oxidation states. I have enlisted all those 5 members, and some elements, they also display the highest oxidation state as a +4. So with this background, we have to move further today is the magnetic properties of all these elements. To study the magnetic moment of all these elements, first of all, again, we have to show the electronic configuration, then we have to arrive at the magnetic properties of all these elements. These properties are very easy to understand provided you listen and see all the explanation very carefully. So just take a look at these magnetic properties. So for those students who did not understand yesterday's electronic configuration, for those it will be very easy to understand. So in the first column I shall write atom number, then the element, then I shall write only the symbol, and the observed electronic configuration I shall write commonly 4f, 5d, and 6s, so that I can write here the number of electrons. It is not necessary to write all the way 4f, 5d, and 6s, and this is always in terms of a xenon core. So first of all, I shall write hurriedly all the required data which is required for our study of magnetic properties. Our first element was lanthanum, atom number 57, then 58, cerium, 59, praseodymium, 60, neodymium, 61, promethium, 62, samarium, 63, europium, 64, gadolinium, 66, terbium, 67, dysprosium, 68, holmium, 69, erbium, 70, ytterbium, sorry, 60, here should be 65, this is 66, this is 67, 68, 69, this is thulium, and atom number 70 is a ytterbium, and 71 is lutetium. So LACE, PRND, PMSN, EUGD, TB, DYSO, ERTM, YB, and LU. So this is our series, constitutes almost 15 members. Now the observed electronic configuration, as that we have seen yesterday, is a 6s2 5d1 4f0. So 56 plus 2 is 56 plus 1 is 7. So 56 plus 2 is 58. 56 plus 2 is 54 plus 2 is 56 plus 3 is 59. This is 2, 4, that is 60. Again 6s2, 4f5, 6s2, 4f6, 6s2, 4f7, 6s2, it should be here 4f8, but because of very small energy gap between 4f and 5d, one of the electron gets exchanged, and now the observed electronic configuration becomes like this. So up to gadolinium, except to that of lanthanum, all these elements having 0 electrons in 5d orbital. So it is again said that it is of little importance whether these electrons contain any d electrons or not. So it is less important whether these electrons contain any d electrons. Now 54 plus 2 is 56 plus 9 is 65. So 2, 10, 66, 2, 11, 67, 2, 12, 68, 2, 13, 69, 2, 14, 70, and 2, 14 here, again 70. But after 4f orbital has been completely filled, the next choice for the incoming electrons will be 5d. So again it becomes 5d1. So all these elements are having again 0 electrons in 5d orbitals. So this fact, as we know, that all these lanthanides, they do display +3 oxidation state because of a principal, major, or common oxidation states. Now, if at all the +3 oxidation state is there, that means Ln +3, Ln stands for lanthanides. Here, if first member lanthanum shows +3 oxidation state, then it should lose all the 3 electrons, so configuration becomes 0. If cerium shows +3 oxidation state, 2 and 1 electron from this, it becomes F1. Praseodymium +3, it becomes 2 electrons and 1 electron here, so it becomes F2. Neodymium +3, loss of 2 electrons and loss of 1 of the electron from 4, so it becomes F3. So if we go on writing like this for all these elements, like this, +3, majority times +3 oxidation state has been considered because it is a major, principal, or common oxidation state. Sometimes during exam, all the lanthanides, they do display dash oxidation state as a major oxidation state. So your answer should be +3 on account of group valency. So if we go on removing the electrons, yesterday I have shown this also. So this is F9, F10, F11, F12, F13, and F14 for lutetium +3. So these elements in their +3 oxidation state are having, this is the outermost electronic configuration. Now, in order to study the magnetic property of all lanthanides, we have to consider the basic idea of magnetic property. As we know, every electron has 2 types of motions. One motion that is known as a spin motion of an electron, another known as the orbital motion of an electron. Spin motion of an electron determines the spinning of electron in a clockwise sense or in an anti-clockwise sense. If we have denoted a spinning of electron in a positive sign, it indicates the rotation of electron in a clockwise sense. If we denote the rotation of electron by a negative sign, it indicates that the rotation of electron in a counterclockwise or anti-clockwise. So normally it is shown as +½ or -½ sign. So these signs indicative of the spinning of electron in a clockwise or anti-clockwise sense. While the orbital motion of an electron gives the shape of orbitals. So due to combined effect of these two motions, every electron acts as a small magnet and possesses magnetic moment. There are majority two types of magnetic behavior exhibited by all these elements. One is known as a paramagnetic moment and another is known as a diamagnetic moment. What is a paramagnetic moment? We are considering the 4f orbital, which are almost 6 in number. So here, these are the 4f orbital. If these orbital contain single electrons or if these orbitals contain unpaired electrons or singly occupancy is there, then under such circumstances, the atom or ion is a paramagnetic. On the other hand, say for example, we have already studied this. If there is a double occupancy of electrons, that means if doubly occupied or absence of unpaired electrons are there, no unpaired electrons are there, under such circumstances, the corresponding atom or ion is diamagnetic. So if we see the outermost electronic configuration of all these elements, then if we try to denote the total number of unpaired electrons, that is small n. Here no unpaired electrons are there. Here, for example, I would like to draw here the 4f orbital. These are the 7 4f orbital. Here, cerium contains F1, that means it contains one unpaired electron, we have to write 1. Then praseodymium contain F2, like this, 2. Neodymium, F3, like this, F3. Promethium, F4. This is like this, 4. Samarium, F5. This is F5, 5 unpaired electron. Then europium, 6 unpaired electrons, like this. 6 unpaired electrons. Then gadolinium, 7 unpaired electrons are there. So 7. Now, after gadolinium, terbium, F8 means like this. 1 orbital gets paired up. So total number of electrons are decreased by 1 unit and hence it becomes 6. Dysprosium, F9, like this. Total number of electrons are again decreased by 1 unit. So 5 unpaired electrons are there. 5. Then holmium, F10, like this. 3 unpaired electrons are there. Here, holmium. 4 unpaired electrons are there. So if we go on adding or pairing these electrons, then we can add the electrons like this. So here, up to gadolinium, 7 unpaired electrons are there. So these are highly paramagnetic. These are also paramagnetic because they contain either 1, 2, 3 or 5 unpaired electrons. So from this one can conclude, except lanthanum and lutetium, all the elements are paramagnetic. So you should remember one word, that majority of the tripositive lanthanide ions are paramagnetic because they contain either 1, 2, 3, 4, 5 or 6 unpaired electrons. So except to that of lanthanum and lutetium, all these elements are paramagnetic and these elements are diamagnetic. So how to calculate the magnetic moment? The magnetic moment can be calculated in terms of a unit, that is known as a Bohr magnetons, and magnetic moment can be denoted by mu s. S stands for spin motion of an electron. A very simple formula is there, square root of n into bracket n plus 2. This formula that we have already studied in transition elements for semester first. Here just we have to put the total number of unpaired electrons, that is n, and we have to take the square root of all these values. For example, if we take for instance the total number of electrons 4, unpaired electrons 4, then I shall put here n is 4, so 4 plus 2, this is, if we solve this, so 6 multiplied by 24, the square root of 24 is 4.90. So just by putting the value of total number of unpaired electrons, we can easily calculate these magnetic moment. So this is about the magnetic moment. Now, how can we show these magnetic moments in some other form? Just take a look at this. For example, see this. La plus 3. Total number of unpaired electrons are 0. Here 0 unpaired electrons are there. Then Ce plus 3, unpaired electron 1. So we have to write here 1. So I am giving a shortcut method to remember all these elements. Then praseodymium plus 3. 2 unpaired electrons are there, as we have revealed from this tabular form. Then Nd plus 3, 3 unpaired electrons. Pm 4. Then sorry, here it is Sn plus 3, 5 unpaired electrons. U plus 3, 6 unpaired electrons, and gadolinium plus 3, 7 electrons. So here in this case, gadolinium plus 3 is highly paramagnetic because it contains maximum number of unpaired electrons. After gadolinium, pairing starts, which reduces the total number of electrons by 1 unit. Now, if we try to write the total number of electrons for terbium after gadolinium, it is having F8. That means 6 unpaired electrons are there. So here, if I write terbium plus 3, 6 unpaired electrons are there. Samarium plus 3, see here. Sorry, dysprosium. F9, 5 unpaired electrons are there. So here dysprosium plus 3, 5 unpaired electrons. See here, dysprosium. Then holmium, 4 unpaired electrons are there. Then erbium, 3 unpaired electrons are there. Thulium, 2 unpaired electrons are there. Then ytterbium plus 3, only 1 unpaired electron is there. And lutetium plus 3, no unpaired electrons are there. So lanthanum, lutetium having 0 unpaired electrons. Cerium, ytterbium, 1 unpaired electron. Then praseodymium, thulium, 2 unpaired electrons. So here, as I have written here, this sequence, the same number of electrons, unpaired electrons, are exhibited by these pairs of lanthanide elements. So I have written here from 57 to 64, and from 65 to 71 I have written in reverse order that exactly tallies with the total number of unpaired electrons, that is n. So I think you have better understand this magnetic moment. So you should remember most of the elements are paramagnetic in nature. Now I shall proceed further with the colored ions for lanthanide elements. Now, as we know, while studying the topic transition elements, we have seen that the color of transition metal ions, or the color of the d block elements, it is the color of the transmitted light. So I have given the sentence that for every absorbed light there is a complementary color for the reflected light. I would like to give you more emphasis on this aspect. For example, say this is a leaflet of a tree which appears to be green in color. Here we know the natural light that we can see today or every day during sunlight. This white light is a combination of 7 different colors, that is V, I, B, G, Y, O, R. That is violet, indigo, blue, green, yellow, orange, red. So when this white light falls on any object, for example, here we have taken a leaf. So almost all the wavelength of for these colors are soaked up or they are absorbed, and only the color that is wavelength that is corresponding to green light that is emitted. So whatever color we can see, it is the green color. It is a color that is produced due to transmitted color, or for every absorbed light there is a corresponding or the complementary color for the reflected light. Say for example, this is a tomato which appears to be red in color. So when the natural light falls on this tomato, violet, indigo, blue, green, yellow, orange, all these colors are soaked up and it can reflect or transmit the wavelength correspond to red color, and hence we can see through our naked eyes a red colored tomato. So for every absorbed light there is a complementary color for the reflected light, and I have shown you the wheel which contains in the first term that for the every absorbed light there is a complementary color. So based on this concept, most of these elements they are having different colors in their tri-positive ions. I am using here the word tri-positive ion. Now this color property is also associated with the total number of unpaired electrons in the 4f orbital. So if 4f orbital contains no unpaired electrons, or if 4f orbital contains one unpaired electron, under such circumstances, the corresponding tri-positive lanthanum ion is colorless. So if 0 or only one unpaired electron is there, then all such ions are colorless. For example, consider lanthanum plus 3. We have seen that lanthanum plus 3 is having no unpaired electron. Just now I have shown you no unpaired electron. So lanthanum plus 3 is colorless. Again, one unpaired electron, it is again colorless. Now cerium is again colorless. If we move further with praseodymium, it contains two unpaired electrons, so it appears to be green in color. Now, three unpaired electrons for neodymium. See here, three unpaired electrons. It appears to be reddish in color. Four unpaired electrons are there. It is somewhat pink, yellow in color. Then for samarium plus 3, 5 unpaired electron, it is only yellow in color. 6 unpaired electrons, europium, is again pale pink or faint pink in color. And for 7 unpaired electrons, that is for gadolinium. Yes, it is for gadolinium. Again, it is pink in color. Now, if we see if we prepare a chart, that means we can conclude that the total number of electrons which are present here 0, 1. That means here, if we try to summarize, here 0 and 1 is there. That means these elements are lutetium and ytterbium. These are again colorless. two unpaired electrons. Two unpaired electrons, again green in color. Then three unpaired electrons, for example, erbium. For three unpaired electrons, reddish color. So from this we can conclude. Again we shall write the series La, Ce, Pr, Nd, Pn, Sm, Eu, and Gd. They are having 0, 1, 2, 3, 4, 5, 6, and 7 unpaired electrons that we have seen already. So when no unpaired electrons are there, or only one unpaired electron is there, it is almost colorless. So this is also colorless. So for two unpaired electrons, it is green in color, praseodymium, then neodymium, Nd plus 3, it is having 3 unpaired electrons, reddish in color, then promethium plus 3, it is pink yellow in color, then samarium, it is again yellow in color, 5 unpaired electrons, europium, pale pink in color, and 7 unpaired electrons, again it is colorless. So you should make a common statement that when the f orbital is completely half filled, then and then the ion is colorless, or if it is empty, it is colorless, or if it is having only one electron, it is colorless. That means rest all other elements are colored. So again, after gadolinium, if we look at the terbium, see here, terbium having the configuration F8, 6 unpaired electrons. So here terbium plus 3, dy plus 3, HO plus 3, Er plus 3, Tm plus 3, Yb plus 3, and lutetium plus 3. So from this one can conclude that the tri-positive lanthanide ions having same number of unpaired electrons having similar color. This is the common statement. Tri-positive lanthanide ions having same number of unpaired electron having similar colors. How it is? Say for example, lanthanum, lutetium, colorless. Cerium, ytterbium, again colorless. Praseodymium, thulium, green. Neodymium, erbium, again reddish in color. Promethium, holmium, pink in color, because they contain same number of unpaired electrons. Samarium, dysprosium, yellow, same number of electrons. Europium, terbium, 6 unpaired electrons, same color, and gadolinium, 7 unpaired electrons, it is colorless. So this is a common conclusion that we have drawn while looking at all this. So you should remember that I want to show you the different colors also. In addition to tri-positive ions, there are also certain ions which are dipositive. They also show certain different colors. See these colors. How fascinating colors are there. Here lanthanum is a colorless, because of which it is not shown. Cerium, again 0 configuration, colorless. Cerium plus 3 is colorless, but cerium plus 4 is having yellow color. Praseodymium plus 3, it is having a color. Praseodymium plus 4, it is having somewhat dark yellow in color. Neodymium plus 3, dark pink in color, but plus 4 is having violet color. Promethium plus 3, pale pink in color. Samarium plus 3 in yellow, plus 2 is red in color. So how these colors are fascinating? The colors are affected only because of the presence of the unpaired electrons in different ions. So europium plus 2 and plus 3. these are again colorless. So this is how they are colorless, colored yellow, pink, or pale pink in color. Again, lutetium is colorless on account of the F0 configuration. There are again certain ions that I would like to show you. See, these are the colors for the lanthanide nitrates in their hexahydrate. That means lanthanum nitrate 6H2O, cerium nitrate 6H2O, then praseodymium nitrate 6H2O. It is somewhat yellowish green in color, violet. So all these 15 members in their corresponding nitrates with their hexahydrate, that means containing almost 6 water molecules. So this is how we can see the different colors. Here again certain statements are given here that I have shown you that due to jumping or promotion of the electrons from one level to another level, the colors are seen very effectively. So colors of lanthanum complexes originate almost from the charge transfer of the charge means electrons are transferred and there takes the interactions. That is a FF. That means 4f orbitals they split up into different sets and the electrons are transferred from one F level to another F level, but in the same electron subshell. So this is how most of the lanthanide ions, that is the tripositive lanthanide ions, are colored on account of they exhibit the different number of unpaired electrons. Also, we have to remember in mind that if a lanthanide ion, tripositive lanthanide ion, if it contains 0, 1 or 7, all these lanthanide ions are colorless. You may be given in exam the different oxidation states for lanthanide ions and you will be asked that whether these ions are colored or colorless, that you have to write. So in order to have a clear idea of this color formation, you should remember only one sentence: 0, 1, 7. These configurations are colorless. You should remember 0, 1, 7. That is La plus 3, Ce plus 3, and Lu plus 3, and Gd plus 3, gadolinium plus 3. These are colorless. So these are the 4 members which are colorless. Rest all other members are colored. So here it is showing only 3 minutes are left. So in conclusion, I would like to show you that, see this, you should remember this shortcut. This shortcut you may not find in any reference book. This shortcut that I have prepared specially for the better understanding of the entire concept. So the same tabular form you can use for the colored ions in addition to this, the magnetic moments also. So once we know the number of unpaired electrons which are present in the corresponding tripositive lanthanide ions, then we can easily calculate the magnetic moment for all these elements also. The same tabular form that I have given you while studying the magnetic moment also. See here, the similar tabular form that I have given you. So this is a same number of unpaired electrons are there, which I have denoted by a letter small n. So you have to write from lanthanum to gadolinium, that is from 57 to 64. Keep a gap here after gadolinium, and then you have to write the other members in this manner. That is terbium, dysprosium, holmium, erbium, thulium, erbium, and lutetium. So this is how all these members or these pairs, they are having similar number of unpaired electrons. So we can correlate this particular parameter with also to color. So this is a colorless, this is a colorless, this is colored, this is colored, this is colored, this is again colored, but gadolinium plus 3 is a colorless. So 0, 1 and 7 configurations are colorless. Rest all other members are colored. They will ask You have to put the corresponding ion under the category whether the corresponding ion is a colored or colorless. And if you understood all these parameters, then it is very easy to understand. In conclusion, you should remember, or now it is fresh in your mind, you have to prepare this tabular form that will enable you for the better understanding of the two properties in a nutshell, that is a colored ions as well as the magnetic properties. So this is how we have completed the 2 points. Again, only 1 minute has left. So you have to click once again the same link and you have to rejoin this Zoom.